This is our tutorial and today's topic is BILINEAR forms. So before starting this topic, please don't forget to subscribe this channel if you haven't subscribed. If you subscribe, then you will get all these videos related and downloaded on the YouTube by me. So must subscribe and avail all these videos and uploaded by me. And if you like, then like and comment me and share it with your friends. Let's start now. We consider first. Consider first. There are two vector spaces or linear spaces, and one is U and other is V. Both are vector spaces. Are vector spaces. Over a field are vector spaces. Over a field F, which can be real or complex. Over a field F. F can be real or complex. If it is real field, then the vector spaces are real vector spaces, and if it is complex, then the vector spaces are complex vector spaces. Now, we define a bilinear form. A bilinear form is a function. A bilinear form is a function from a set of elements W. W is the direct sum of U and V. It is the direct sum of U and V. From the elements W to some from two scalars to F, the field F, where the vector spaces are divided. So the same field, they will be the bilinear form is also the range A also transform all the elements of W. The bilinear form transform to the field, same field, real or complex, on which U and V are defined. So there needs some condition also. In such a way, this function is defined in such a way that each element of W, each element of W, we are taking alpha, beta. These are alpha, beta. We are taking. Each element of W must be two-dimensional, which is a direct sum of two vector spaces. So the bilinear form is signed in such a way that Each element of W must be must be assigned a scalar. uh, Scalar means on the function on the field A. Scalar, this belongs to the field A, where the uh, vector spaces U and V are defined. To A scalar this will be F. F is the bilinear map alpha beta. So the function of the function on the elements alpha beta of W must be scalar. So uh, so for each element of W, each element alpha beta, any element, the scalar, the bilinear map assigns a scalar on A. So in a way that these two conditions must be satisfied. One is 1 A alpha 1 plus B alpha 2 beta is equal to A F alpha 1 beta plus B alpha 2 yes, F alpha 2 beta. Here alpha 1 and alpha 2 belongs to alpha 1, alpha 2 belongs to alpha, and A and B are belongs to A. This first condition must be satisfied, and the second condition is that and if alpha A beta 1 plus B beta 2 must be equal to A A alpha beta 1 plus B alpha A alpha beta 2. So there is a difference between the Hilbert space, you can say here is the difference between the norms Hilbert space function that here for the second dimensional um, square components we have to take conjugate, but in the bilinear map we don't need to take conjugate. It is simply we will take A and B. If A and B belongs to F, which is complex, then also we don't need to take conjugate. So here AB belongs to complex field, and beta 1 and beta 2 belongs to beta. So these are two conditions for the bilinear form. Now, what is the matrix of the bilinear form? Matrix bilinear form. Important one it is to evaluate the matrix on bilinear form. How we can uh, generate a matrix on bilinear form. We'll take any. We will consider let a V is a V is n-dimensional, finite dimensional or n-dimensional vector space. V is a finite dimensional. We are taking n-dimensional vector space. N-dimensional vector space. Then it must have a ordered basis, and we are taking the ordered basis as ordered basis ordered basis we are taking V or beta, which is element which basis elements are alpha 1, alpha 2, and so on. The last basis element is alpha n. So what we need to do to generate a matrix, we need to take a bilinear map from uh, uh, on V in such a way that we take a bilinear map A on the V such a way that it actually V, but it must be actually beta must belongs to V on the basis of V. So it will be the bilinear form from beta plus beta to the field F or scalars. So how it map? It is mapping. It will be in this way. F alpha I alpha j is equal to, we will get different values for different alphas. So we are now denoting it as ij. This is j, ij. If we take 1 2, then we will get 1 2 uh, first to second element. If we take 1 1, then we will get first element of the matrix. In this way we will represent where I and j both, where I and j both goes from 1 to n. There are n elements, that's why I to n. And j also 1 to n. So there are n elements, so we will get n cross n matrix. We must get n cross s matrix in this way. There will be the matrix. We can represent this matrix by this way on the function a by the order basis beta. We will have generated this. We will denote it to the matrix in this way. All these elements will be a11, a12, and in this way a1, and the second row, third row, and the last row will be an1, an2, and last element will be a. Here we are getting a square matrix of n order. So this is the way to generate a matrix on a bilinear form. So what is the rank of the bilinear form? So any rank of any bilinear form, rank which is a function, rank of any bilinear form. If you know the uh, transformation, rank of transformation is the rank of the matrix induced by the transformation, linear transformation. And similarly, rank of a bilinear wave is the rank of the matrix induced by the bilinear map. Rank of the matrix is the rank of the bilinear map. Of the matrix A induced by the order basis beta equal to the rank of the it is called rank of bilinear map. Okay. Rank of bilinear map. Yeah. Yes. You have understood. And symmetric bilinear map. What is the symmetric bilinear form? Bilinear form actually. What is symmetric bilinear form? If the matrix induced by the bilinear form is symmetric, then the bilinear form is also symmetric. So I will give you an example. Okay, very easily understand what is symmetric bilinear form. Symmetric bilinear form. Bilinear form. So this example will use this topic. So let's use this example. Here, yeah, the bilinear map is defined on a second dimensional space R cross R to R. So how it is defined? So it is defined here. This is two dimensional, two dimensional. This is two dimensional, and this is two dimensional. So you can take, you have to take two dimensional, two components for validating. We are taking x1, y1 for the first uh, Cartesian space or two dimensional space, and uh, for second we are taking x2, y2. So you can understand how bilinear forms can be represented. So it will represent just only one scalar r. The importance of bilinear form. It is given that it will be x1 y1 plus x2 y2. So here you can look this value we will get after putting the coordinate just only on the field r. So it's only one dimensional values or scalar values. So how the matrix F B F B can be generated? So we have I have already discussed this. We need the ordered basis. Here ordered basis given. Ordered basis given. Ordered basis given. Beta is equal to there for the first one they were given 1 minus 1 and for the second one is given 1. So we are looking at the basis element, ordered basis for the domain space. So we now use this to uh, the matrix on the bilinear form. So how we can calculate? We have to remember this. So I'm erasing this component. I'm just keeping on the just the defined bilinear form and the ordered basis. We have to first calculate if we are denoting this is alpha 1, this is alpha 1 and this is alpha 2. So there are two elements, the basis elements as I have said. So there will be first we will take alpha 1, alpha 2. First we will take alpha 1, alpha 1. Then we will get the element A11. What will be the value of this? We will get 1 1. So alpha 1 means there will be there will be here this will be changed by x1 and y1. There is x1 y1 since here we have taken here alpha 1, so it will be alpha 1 alpha 1. So alpha 1 is given 1 minus 1, so it will be 1 multiply minus 1 plus 1 multiple minus 1, so it will be minus 2. Understood? In this way, if we take f alpha 1 alpha 2, here we will get 1 2 element, first row second element. So here we will take both x1 y1 x2 y2. First we will get minus 1, 1 multiple minus 1 minus 1 plus 1 multiple 1 is 1. So we will get here 0. Now we will change. Uh, we'll keep alpha. Now we'll take alpha 2 and alpha 1. Here we'll take alpha 2, alpha 1. These are the possible taking. There are two uh, two bases, and we have to take two bases, any one from them, any two from them. There will be chances probability permutation will be 2 factorial by 0 factorial. They can interchange also, not in this way. So there are two positions, and anyone can go to the alpha 1 get go to the first position, or alpha 2 go to the first position. So both have two chances. So 2 cross 2, there are 4 chances. So we have 4 elements in this way. So and there will be the element A1 will be, here we will get now it remains same. If you alternate x2 y2 x1 y1, it will be same. So here it will be same element will get 0. And last, if alpha 2 will take, then we will get a 2 element. Here it will be x2 y2 plus x2 y2, and x2 y2 will be 1 plus 1. So 1 plus 1 is 2. There are 4 elements we have found. Now we can generate the matrix on the bilinear form. So in this way we can generate, let's see this, induced by the ordered basis beta, this matrix. So first element a11 is -2, a12 is 0, a21 is 0, and a22 is 2. So what is important thing is to that the non-diagonal elements are similar. So it is a similar matrix. So the the function, the mapping is also similar. So bilinear form is also similar. This is similar matrix. So the map is also similar bilinear matrix. Symmetric, similar matrix, not symmetric matrix. Symmetric matrix. Symmetric matrix, and then map is also symmetric bilinear form. Symmetric map. So matrix. So the bilinear form is symmetric. Symmetric bilinear form. So I hope you like this video. If you like this video, share it with your friends. And if you have not subscribed, then subscribe this channel. Thanks for watching. Have a good day.